Right. Okay. Yeah. Many thanks. So yes, I'm at ESTEC since 2008. Prior to which I was in planetary sciences at the Open University, working on things like Rosetta and the Huygens lander to Titan. And in 2008, I joined ESA to work as an instrument systems engineer, initially on EXOMARS 2016, and then on the EXOMARS rover, Rosalind Franklin, and these days, last 5 years or so, I've been working on future mission studies and technology developments. So this is kind of a little bit of a trip back for me to the rover when I was working with Philippe and many other colleagues in France and elsewhere on interfaces for the payload instruments on Rosalind Franklin. So EXOMARS, just to recap, we have operating happily in orbit around Mars now, the Trace Gas Orbiter with its 4 instruments and its data relay capability, which is being used for Curiosity and Perseverance. Much of the data comes via the JPL provided Electra radio on TGO, and that is due to be used also for Rosalind Franklin from after it lands in 2030 for data relay for our operations there. So what are we aiming for with Rosalind Franklin? Well, of course, it's looking for biomarkers of preserved life from the past of Mars. We know that Earth and Mars started off with quite similar conditions in terms of bodies of water, hydrothermal environment, etc. But then over time, due to Mars being smaller and atmospheric loss, the conditions diverged, and the amount of water at the surface of Mars decreased. But perhaps we still have areas where biomarkers from potential past life may have been preserved in rocks close to hydrothermal activity, for example, or where water has been flowing at the surface in the past. So Rosalind Franklin will be looking at habitability as evidenced in the surface environment and the rocks, and the state of preservation of organic biomarkers, looking at the particular rock samples with extremely sensitive instrumentation at the where biomarkers may have been preserved. So we have a lot of hardware in the clean rooms at the moment. Some of it has been ready for quite a few years. So here's the carrier module, which is led by OHB in Germany. So that's there for taking us from after launch for the cruise to Mars, and then it separates from the descent module, which was previously provided by the Russian cooperation, but now that's had to be replaced with European-led elements, as is also the case for the lander there, and folded up inside the landing platform is the flight model rover, which is currently in the clean room, undergoing some refurbishment and upgrades to be ready for launch in 2028. So here's a view showing the concept for deployment of the rover onto the surface, or egress as we call it. This shows the previous design, but the new lander is being built, and it will look quite similar, but will not have a long-term operating payload after landing on the surface. There will just be some initial measurements at landing, and then that will cease to function once the rover drives off, and then we have our surface mission with the rover, which is in reality, if I was standing next to it on the ground, the top of the panoramic camera would be just a little bit higher than me, about 2 meters above the ground. So we're building a new lander. So the concept of operations, very very briefly, very simply, is we find outcrops, promising-looking outcrops of rocks, and then those, of course, have been close to the surface, at or close to the surface for a long period of time and subjected to sterilization by ultraviolet radiation, oxidants, chemical oxidants in the atmosphere, and ionizing radiation over billions of years, depending on the geological age of the landing site. So the strategy is to try to access samples where organic biomarkers may have been preserved by stepping back from such outcrops and then using our unique drilling capability down to up to 2 meters depth to access samples and bring them back inside the rover for very sensitive analysis. So in order to do this, we have obviously a surveying and target identification activity that the payload has to support, then acquiring the samples and then analyzing the samples. So the logic of the payload is kind of in the order that they're shown here. So we have a panoramic camera with actually 2 channels. We have wide-angle stereo camera, stereo pair with geological filters. So that's the white part that you can see at the top there. And then there's a high-resolution stereo camera to focus on a smaller area, say an outcrop in the distance. Then we have, underneath the panoramic camera, we have a replacement for one of the 2 previous Russian instruments that were on the rover had it been launched in 2022. So that's been replaced by a UK-led infrared spectrometer called ENFIS, which is Welsh for rainbow. Okay, it's not an acronym; it's Welsh for rainbow. and interesting fact: the vast majority of the upper surface area of the Rosalind Franklin rover is made in Wales. Okay, and the reason for that is you've got ENFIS on the optical head on the top there, and all the cover glass on the solar cells is from a factory in Wales, and the fiducial markers and the PanCam calibration target are also led by the University of Aberystwyth in Wales. So any Welsh people here? No, okay. Right. So anyway, I digress. Back to the story. So we have Clupy, close-up imager, which is a Swiss-led camera, and that's mounted on the drill box, which is the black box that you can see here, and that goes up and down. I'll show you an animation in a moment. And that can, while we're roving, look at what we're roving over, and then when we get close to an outcrop, we can get close-up images of where we're going to drill, and also monitor the drilling activity as it's underway. So what's next? Yes, the Wisdom ground penetrating radar that Philippe worked on. So that has antennas at the back, I'll show you, and electronics inside. And as we rove over, and we can do a kind of a raster scanning of the surface to get subsurface imaging of the rocks to try and find this buried bedrock that you saw in the cartoon just now as a target for drilling. So we hope to be able to see, layers of material. So the difference between granular material and solid bedrock. Then we've got the drill, and it incorporates an infrared spectrometer, so we can actually measure the minerals during the drilling process. And then once we have a sample delivered to the analytical laboratory inside the rover, which comprises 3 instruments, except it's actually 4 because one of them is 2 different types of measurement technique. So the first one is a visible and infrared microscope measuring the minerals in many different spectral channels. So we have a crushed sample that is then imaged on a carousel by Micro Omega. That's French-led instrument, as is Wisdom, by the way. And then the Raman spectrometer starts to detect interesting grains with potentially organic molecules incorporated. And then the most sensitive instrument in terms of measuring organics is MOMA, and that has two modes: a laser desorption mass spectrometer and then a pyrolysis derivatization GCMS device. So that's a collaboration between Germany, France, and the US. So here we are. I can perhaps pause the animation if, but no, let's keep it at the rate it's playing. So there's the radar antenna. You see the camera and the spectrometer on top. The drill box is stowed in this view here. Radar scan of the subsurface. So perhaps, having found an outcrop here, we rove back and identify some bedrock to drill. So here's the drill box. This is a Klupi image there. Then you'll see the drill box rise up and rotate. And here we've got the electronics for the drill and also the MAMIS spectrometer on that side. And here's Klupi, the close-up imager. Actually has three fields of view with a couple of mirrors that allow it to see forwards. And this is the view down. This is a panoramic camera of the white box here. Pan-cam calibration target I mentioned there. There's one of the Klupi mirrors to look sideways. So here we are. We're targeting this spot for drilling. The sample is eventually going to go into the inside of the rover through a drawer that's going to pop out there. So here we are, showing penetration into the surface and drilling, and we have several several segments of this this drill that can be strung together to go down to 2 meters. Which will take several sols. Klupi is able to get a good look at what's coming out of the borehole through the spoil pile around the drill hole here. So here the sample is coming up inside the drill, and the drill rotates. Pops out. And there's a sort of a spoon that can drop into there. And if we don't like it, we can actually drop it on the ground. But all being well, we draw it inside the rover. And who knows whether it'll just be a solid lump crushed up already or somewhere in between. But anyway, it goes to a crushing station and then can be dosed into a carousel with various ovens as well as a refillable container. But first we take a look with pan-cam, Klupi. So here's a view of the sample in the sample container. Be able to do this several times during the course of the mission, of course. Oh, come on. I didn't press pause. Let's see what's happened.
Can you lower the volume of the computer?
Yeah, sure, yeah. Let's see. There we go. There we go. I think we're back in action. Yeah. Oh, no, that's gone back to the beginning again. Bear with me. Maybe I'll move on to the next slide. Anyway. Let's see, or maybe I'll fast forward to here. Yeah. Okay. Okay, so it's gone inside the rover. There we are, to this thing, which is called the Analytical Laboratory Drawer. This is the flight model complete. Now, even many people who work on the project can't actually identify what everything is in this picture. It's a very, very complicated beast. It's about this size. So this is including the crushing station, the dosing station, the carousel, which is in a very clean area, a volume here called the ultra clean zone. And then you have the experiment units of the micro-omega instrument, the Raman laser spectrometer, and the MOMA instrument. And those are all integrated into here. And then this is inside the body of the rover, behind the white radiator that you can see at the front of the radiator. And so there's a carousel here with dosing stations, and so we would start off putting a crushed sample into the refillable container, imaging it with micro-omega. So we get a first idea of the minerals, whether there are any particular grains of interest, and then this carousel can then rotate to be interrogated by the laser of the Raman laser spectrometer, and that can look at a track across the refillable container. Then that can be zapped by the MOMA laser desorption mass spectrometer, so we can get a number of samples, and perhaps the Raman and MOMA lasers are directed by identifying grains of particular interest in the data from micro-omega. And then samples can be dropped from the same drill sample, because we don't put everything into the refillable container. So from the same drill sample, we can also dose one of the ovens for analysis of the sample by the MOMA GCMS. So here's the rover flight model in the clean room, folded up. So the mast and the solar arrays are all folded there. You can see the wheels in the stowed position. There's the drill box. Can't quite see Wisdom at the back there. So this is in Torino, and every week we get an update as to how things are going with the refurbishment. An important aspect of the mission is the landing site, of course, and we're aiming for clays, and at the site for Rosalind Franklin, those are believed to be older than the sites that Perseverance and Curiosity are investigating. So we're hoping that will give us some of the best chance to identify biomarkers from the Martian past. Here's a view of where the Oxyoplanum landing site is, on the edge of Chryse Planitia. The red areas have been identified as containing hydrated minerals that are of interest for preservation. And there was a whole sort of almost crowdsourced mapping activity to look at the high-resolution data of the middle of the landing ellipse to identify and get ready for operations. So we don't know exactly where we'll land, but if we land somewhere around here, then we've already got a geological map to help us decide which direction to rove initially for the best science. So you can download this map here. Baseline launch is in 2028, September, October, with arrival in 2030. And then there's a backup launch in December 2028, with arrival actually a bit earlier in 2030, because it goes on a different trajectory. So this is a plot courtesy of JPL. So the launch is provided by NASA. They have other contributions to the mission as well. So fingers crossed for 2028. Things are on track to launch Rosalind Franklin finally. So the mission science is still compelling. We'll go back in time to look for Martian biomarkers, really get deep into the Martian surface, deeper than ever before. And we've got a great payload lined up to do that job. And so we hope to make fundamental discoveries in organic chemistry, life sciences, comparative planetology, etc. So looking forward to a great mission in just a few years' time. And maybe I'll get to visit the Science Operations Centre while the mission is running. That's in Turin as part of the Rover Operations Control Centre. Thanks very much.
I think we have time for questions, so please.
What is the state of the launching devices, rockets and the platform, please?
NASA is in charge of procuring the launcher, so the launcher is not officially selected yet, but that's procurement in progress, and the lander is under construction at the moment, construction and test. The UK is UK-led landing platform at Airbus in Stevenage, but with contributions from industry around Europe. I know the egress ramps are from Poland, for example. Many other bits and pieces from elsewhere, and some hardware that was originally on the EXOMARS 2022 landing platform that was European has been dismounted and will be repurposed on the EDLM, as it's called, for 2028.
You're using the same transportation mechanism for every sample you drill, right? So the spoon that is retracting from the drill.
The spoon, yes, that's correct. Yeah.
Do you have a model of how risky the cross-contamination is from one sample to the other?
Yeah.
Because you only have one clean spoon in the beginning.
Yeah, that's right. So indeed, there are cross-contamination requirements, and so that's been tested. I forget what the numbers are, but it's I don't know, a couple of % or something cross-contamination from one sample to another. We do have inside. We have 2 separate funnels of the dosing station, so it's possible to split off separate samples. So if we use one dosing mechanism, then the other one is clean for the next run.
But you could, for instance, image the spoon once it's emptied, drawing it out again, and having quickly taken out a picture of the.
In principle, yes. That would be an operational decision as to whether we wanted to spend the resources doing that. Yeah.
There is no mixing in the sample, so that would say the cross-contamination is remaining on the bottom of the.
That's correct. Yes.
And so you are analyzing on this surface, and you have done this mixing, which is.
Yes. Yeah. It's just.
That the risk is.
It's whatever dust is stuck to the surface. In other words, yeah.
You've got a lot of mechanical moving parts. Is there any concern about dust ingressing that would then stop things moving?
Yes, indeed, and that's the sort of thing that is required to be mitigated and tested. There's an environmental specification that includes dust aspects. Things inside, depending on where they are, can be behind so-called HEPA filters, which are there for planetary protection reasons, but also protect from dust. So. And dust also lands on the rover over time, of course. That's to be expected, and that can change the thermo-optical properties of the surface, so that's to be taken into account. Yeah.
A question beyond Rosalind rover. Are you allowed to share some hot news about Mars from the ministerial meeting?
Well, in terms of Rosalind Franklin, the news is positive. I would say the implications from the ministerial, we can't comment yet because it needs to, the amount of money committed, we now need to update the plan to define what we can do and what the member states would like to do with the money pledged. So in the coming weeks and couple of months, that should emerge, I expect. So watch this space. But for Rosalind Franklin, we're on track for 2028.
Last question. Yeah.
How many drilling operations would you contemplate doing during?
We have what we call experiment cycles and vertical surveys. So an experiment cycle is where we take perhaps one drill sample from close to the surface and then move on and take another. A vertical survey is multiple samples at one location. And so I think in the original baseline mission, it's 6 experiment cycles and 2 vertical surveys, if I remember correctly, over 218 sols.
MOBA is limited in the number of samples that you can analyze.
Yes, because we have a finite number of ovens. And 28? Yeah, something like that. And so eventually you start having to reuse ovens if you really want to do that, and then you've got more cross contamination, of course. But the refillable container can be used an arbitrary number of times. So.
Thank you.
Okay.
Thank you very much, Louis.